Welcome to Lecture 15, Section 3.2 of the text Elements of Modern Algebra by Gilbert and Gilbert 8th edition. This is Dr. Gilbert Eyabi. Section 3.2, Properties of Group Elements. Subsection 3.2.1, Theorem. We shall look at some properties of group elements. Let G be a group with respect to the binary operation star, where star is multiplication. Then we have the following properties. Number one, the identity element E in the group is unique. Property 2, for every x in G, the inverse of x is unique. Property 3, for every x in G, the inverse of x is x. Property 4, known as the reverse order law. For every xy in G, xy parenthesis inverse equals y inverse times x inverse. And property 5, the cancellation laws. If a, x, and y are elements in G, then either of the equations ax equals ay or xa equals ya implies x equals y. I.e., I can cancel out my a, I can cancel out my a. And just very quickly, the proof of this is very easy. We know that if G is a group and A is an element in G, then A inverse exists. For this equation, multiply from the left by A inverse, and that should give you x equals y, since A inverse is E. Similarly, for this equation, multiply from the right by A inverse, then A inverse would give you E, and so x equals y. So the proof for property E is straightforward, and I'm going to leave that as a simple exercise for serious students. Now let's go back and look at a few of these properties and their proofs. Property A, the identity element E in G is unique. Suppose E1 and E2 are identity elements in G. To prove uniqueness, we must show that E1 equals E2. But E1 equals E1 times E2 because E2 is an identity element. But E1 times E2 also equals E2 because E1 is an identity element. So basically, we have shown that E1 equals E2, and that means the identity element in G is unique. A very simple, straightforward proof. The proof of property 2 is a little more interesting to me. Let X be an element in the group G, and do not forget G is a multiplicative group, i.e. the binary operation star on G is multiplication. Suppose y1 and y2 are inverses of x. Just like we did in part A above, we have to show that y1 equals y2. That is how we prove uniqueness. But y1 an inverse of x, by the definition of the inverse of an element, that means x times y1 equals the identity E, and that equals y1 times x. And y2 an inverse of x means that x times y2 equals the identity, and that equals y2 times x. I've called this equation 1, that is x y1 equals E. I've called this equation 2, that is y1x equals E. I've called this equation 3, that is x y2 equals E. And I've called this equation 4, y2x equals E. I'm going to use a combination of these equations to prove that y1 equals y2. So I start on the left-hand side with y1. y1 equals E times y1 by the definition of the identity element E. But by equation 4, E equals y2x. So that equals y2x times y1. But by associativity in groups, go back and check the definition of a group. Associativity holds in every group. By associativity, that gives us y2 into x times y1. But x times y1 by equation 1 is e. So that gives us y2 times e. And by the definition of the identity element, y2 times e equals y2. So we have just proved that y1 equals y2, and therefore the inverse of x in G is unique. Now observe that properties 3 and 4 are very straightforward. You want to prove that the inverse of x is x, and you want to prove that the inverse of x times y is y inverse times x inverse. All you have to do here is recall that A inverse equals B if and only if AB equals E equals BA, right here. A inverse equals B if and only if AB equals E equals BA. So to prove that A inverse equals B, what you have to show is that A times B is the identity and B times A is the identity. Once that is done, we can conclude that A inverse equals B. Use this concept to prove properties 3 and 4, and property 5, we already talked about it. It is straightforward. Subsection 3.2.2 Theorem. Equivalent conditions for a group. Let G be a non-empty set that is closed under an associative binary operation called multiplication. Then G is a group if and only if the equations AX equals B and YA equals B have solutions X and Y in G for every AB in G. i.e., the forward direction says, suppose G under the binary operation multiplication is a group, we have to show that the equations AX equals B and YA equals B have solutions X0, Y0 respectively for every AB in G. The reverse direction. Suppose the equations AX equals B and YA equals B have solutions X0, Y0 respectively. We have to prove that G under the associative binary operation multiplication is a group. If you go back to section 3.1, you will see the definition of a group. In other words, we have to show that G under this associative binary operation multiplication is closed. 2, we have to show that G is associative. That is already given because we are told that G is a set under an associative binary operation multiplication. 3, we have to show that G has an identity element E. And 4, we have to show that G contains inverses, i.e., for every X in G, X inverse exists. If we can verify the forward direction and the reverse direction, then we can conclude that G is a group if and only if the equations AX equals B and YA equals B have solutions X, Y in G for every AB in G. The complete proof is found on pages 153 and 154 of your text Elements of Modern Algebra 8th edition by Gilbert and Gilbert. Subsection 3.2.3 Definition. The product notation. Let n be a positive integer n greater than or equal to 2. For elements a1, a2, right up to an in a group G, the expression a1 times a2 times an is defined recursively by a1 times a2 right up to ak plus 1 equals a1, a2 up to ak in parentheses times ak plus 1 for k bigger than or equal to 1. For example, if n equals 5, then we're saying that a1 times a2 times a3 times a4 times a5 equals a1 times a2 times a3 times a4 parentheses times a5. Subsection 3.2.4 Theorem, the generalized associative law. Let n be a positive integer, n greater than or equal to 2. And let a1, a2 right up to an denote elements of a group G. For any positive integer m such that m is greater than or equal to 1 and m strictly less than n, a1 times a2 right up to am, multiply all of that in parentheses by am plus 1 right up to an simply gives me the product from a1 up to an. In other words, I can get rid of the parentheses and that would not affect my solution. So basically what we're saying is a1 right up to an, the product of these times the product of am plus 1 right up to an, the parentheses can simply vanish and that gives me the product from a1, a2, am plus 1, an minus 1 right up to an. Proof. For the proof of this theorem, we use the principle of complete mathematical induction on the positive integer n where n is greater than or equal to 2. I will refer you to page 155 of your text Elements of Modern Algebra 8th edition by Gilbert and Gilbert for the proof. Subsection 3.2.5 Definition Integral Exponents. Let G be a group with respect to the binary operation written as multiplication. Then for every element A in G, we define the non-negative integral exponents by A raised to the power 0 equals the identity element E, A raised to the power 1 equals A, and A raised to the power k plus 1 equals A to the k times A for every positive integer k. We also define negative integral exponents by a to the negative k equals a to the negative 1, all of that parentheses, raised to the power k for every positive integer k. Let's take an example where we shall apply the idea of non-negative integral exponents and the generalized associative property. Let G be a group with the binary operation written as multiplication and in which x squared equals e for every x in G. Prove that G is abelian. I want you to observe this unique property of the elements in our group G. If x is in G, that means x squared equals e, and x is arbitrary. Let's go ahead and prove this. Proof. Let G be a group in which x squared equals e for every x in G, and of course our binary operation is written as multiplication. Required to prove G is abelian, i.e. xy equals yx for every xy in G. Now let's start the proof. It's actually a very beautiful proof, so make sure you follow me very closely. X times y equals x times e times y by the definition of the identity element. It's like it's not here because x times e is just x and e times y is just y. So I can write my xy as x times e times y. But x is an element in G, y is an element in G. G is a group. And by the closure property, x times y is in G. But if x times y is in G, then x times y, all of that squared, has to be equal to E, because we are told that x squared equals E for every x in G. So I can write E as xy squared. X is in G, y is in G, x times y is in G by the closure property, and x squared equals E by the definition of elements in G. So I replace E by x, y, all of that squared. Now I can write xy squared as xy times xy by the definition of non-integral exponents. That will be xy raised to the power 2 minus 1 times xy. Right here, a to the k plus 1 equals ak times a. A to the k is simply a to the k plus 1 minus 1. So this gives me x times xy times xy times y, and I have so many parentheses around here, and I can use my generalized associative property to move the parentheses around, and I'll pair x and x, y and x, y and y, and that gives me xx in parentheses, yx in parentheses, yy in parentheses. Again, that is by the generalized associative law. But again, x times x is the same as x squared by the definition of non-integral exponents. Yx stays the way it is. Y times y equals y squared by the definition of non-integral exponents. But what is x squared? X is in G, so x squared is E. What is y squared? Y is in G, so y squared is E. By the definition of the identity element E, E times yx times E is simply yx. We just showed that xy equals yx for every xy in G. Therefore, my group under the operation defined as multiplication is abelian. And we're done. Beautiful proof. Subsection 3.2.6 Theorem. Laws of exponents. Let x and y be elements in a multiplicative group G, and let m and n be integers. Then we have these properties. Proof. We would use the principle of mathematical induction on n. Let m be an arbitrary but fixed positive integer. Construct a mathematical induction proof on n. You will observe that there are three cases for n, since n is an arbitrary integer. N could be equal to 0, n could be in z plus, or n could be in z minus, or we can say negative n is in z plus. We perform induction on n. The proof is on pages 157 to 158 of your text, Elements of Modern Algebra by Gilbert and Gilbert 8th edition. I would leave that as a simple reading exercise for serious students. Subsection 3.2.7 Laws of Multiples. Most of what we have seen so far had to do with the group G as a multiplicative group. What if G is an additive group? Let x, y be elements of an additive group G, and let m and n be integers. Then the laws of exponents, which we saw in Theorem 3.2.6, translate into the laws of multiples as follows: A, B, C, and D. Again, let m be an arbitrary but fixed positive integer. You are required to perform mathematical induction on n, just like we did in Theorem 3.2.6 above. I would leave that as a simple exercise for serious students. Before I conclude section 3.2 and move on to section 3.3, I want to leave you with two very interesting problems. Problem number one, define the relation R on the group G where your binary operation is multiplication by X is related to Y if and only if there exists an element in G such that Y equals A inverse XA for every XY in G. G is a multiplicative group. I want you to show that R as defined is an equivalence relation and go ahead and find the equivalence class of an arbitrary element X in G. Nice little problem. Number two, I want you to prove that the multiplicative group G is abelian if and only if AB inverse equals A inverse B inverse. Another very short, beautiful, elegant problem for you to prove. Thank you. I will see you in section 3.3 subgroups. God bless you.